I'm Maria, and I've been using Qiskit to understand quantum thought experiments by turning them into quantum circuits that you can run on a quantum computer. Today I'm going to explain the quantum Zeno effect. Zeno of Elea was an ancient Greek philosopher who lived in the 5th century BC. Zeno is well known for his paradoxes, which have caused a lot of debate and discussion throughout history. Zeno's arrow paradox seems to suggest that motion should be impossible. Zeno imagined an arrow flying through the air, like this. And then he reasoned that at each instant that the arrow is flying through the arrow is stationary. So if the arrow's motion is made up of lots of individual instants where it's stationary, then how can the arrow ever be moving? This apparent paradox can be resolved by realizing that time is not actually made up of individual instants. If we take some time interval and look at the motion of the arrow in that time interval, it will have some finite non-zero speed. And we can make that time interval as small as we like, all the way down close to zero, and the arrow will still have a non-zero speed. This is the fundamental idea behind calculus, where we take time intervals all the way down close to zero and then see the velocity of an object. We can calculate that at a given instant in time. Now, what happens if we make our arrow quantum and observe the motion of a quantum system over very small time intervals? Well, in 1977, George Sudarshan and Baidyanath Misra from the University of Texas wrote a paper entitled The Zeno Paradox in Quantum Theory. Incidentally, the same thought experiment was proposed some years earlier by Alan Turing, and so it's also known as the Turing paradox. Alan Turing is well known for his contributions to cryptography, and he also cracked the Enigma machine to help win World War II. Sudarshan and Misra considered an unstable radioactive particle, which has some probability of decaying. And they used quantum theory to calculate that if you continuously observe this unstable particle, then it should never decay. This seems like a paradox, much like when you continuously observe Zeno's arrow, it seems that it should never actually be moving. Now, the key difference between the quantum thought experiment and the original Zeno's arrow thought experiment is that observation does actually affect a quantum state, whereas it has no effect on an arrow flying through the air. Let's pretend that this arrow is representing the block vector on the block sphere. So it's representing the state of a qubit. When the arrow is pointing up, this is the 0 state of a qubit, and when the arrow is pointing down, this is the 1 state of the qubit. When the arrow is in between 0 and 1 pointing sideways, then it's a superposition of 0 and 1. And when we measure the state of the qubit, then the qubit state is projected into either the 0 state or the 1 state with some probability. Now, let's imagine that our qubit is evolving over time from the 1 state to the 0 state. So our qubit starts in the 1 state, and if we don't do any measurements, then it will just evolve all the way to 0. But if it starts in the 1 state and then we let it evolve for a short time, and then we measure it, then it will have a high probability of being projected back into the 1 state. And then if we measure it again after it's evolved again, it will also have a high probability of being projected back to the 1 state. So by making our measurements more and more frequent, we can ensure that our qubit stays in the 1 state with as high probability as we like. So just as through continuous measurement, we can prevent our qubit from evolving from the 1 state to the 0 state, we can also use continuous measurement to prevent an unstable particle from decaying. While the ability to freeze a quantum state using continuous measurement may seem strange, the quantum Zeno effect does not lead to any known inconsistencies, and it has been demonstrated experimentally. In fact, we can use our Qubit model of the atom that may or may not decay to test the effect ourselves using Qiskit. So we're going to start with our qubit in the 1 state to represent our atom in its excited state, and this will evolve to a qubit in the 0 state, representing our decayed atom, which is in its ground state. And to evolve our qubit from a 1 to a 0, we can apply a series of X rotation gates. So we encode them using the Rx gate in Qiskit, and you can see here we have used 20 time steps. So through a series of 20 X rotation gates, we rotate our state from a 1 to a 0. And we use an X gate at the beginning to initialize our qubit in the 1 state. So now let's check that if we start with the 1 state and apply these 20 X rotations, we do actually end up with the 0 state at the end. So we can check this by running the quantum circuit in a simulator, and we can see the histogram showing the output, and we can see here that it has 100% probability of getting the outcome 0, so we have successfully rotated our qubit state from a 1 to a 0. Now let's have a look at how this state is evolving over time at each time step. So here we're going to plot the probability of the state being a 1 as we add more and more time steps. So you can see the plot here. So we have the probability of measuring a 1 as we add more and more time steps, and it starts off at 1 and then goes all the way down to 0 after our 20 time steps. So that's how the qubit state is evolving over time. What happens if we instead add measurements after each of our X rotation gates? So now every time the qubit is rotated a small bit by one of the X rotation gates, we're going to apply a measurement so that we are approximately continuously measuring the qubit state. So I'll just run this code to run the simulator for our 2 circuits, one without the measurements after each rotation gate and one with the measurements after each rotation gate. And we can see the outcome in this plot. So we have this blue line is the same as before, but now you can notice this green line here. This shows the probability of measuring a 1 with the Zeno effect. And you can see that we have actually managed to freeze the state to be close to 1 because our probability of measuring a 1 stays close to 1 even after 20 time steps. So this plot is showing us the quantum Zeno effect's ability to freeze the state of the qubit in the 1 state. So we have so far been running the code on the Qiskit simulator, but we can also run it on a real IBM quantum computer. I've tested it with the IBM Q RMonk device, which is a 1 qubit quantum computer. And so that we don't need to wait for it to run, I've just used a plot that I created earlier from running this code on the real quantum computer, and we can see what happens this time. The plot without the Zeno effect actually looks very similar to before, and with the Zeno effect we can see we have this other plot which has this kind of zigzag pattern due to the noise of running the code on actual hardware. So we can still see this difference between using the measurements for the Zeno effect and not having them without the Zeno effect when we actually test this out on actual quantum hardware. I created a game which uses this function called a quantum freezer to see how many qubits you can successfully freeze. So we are going to define this function where we can have as input the number of qubits that you want to try and freeze, so that you want to try and keep in the one state, and the number of time steps that you're going to use. And now let's have a go at seeing how many qubits we can freeze using the quantum freezer. So let's try this. So let's say we want to try and freeze 100 qubits. And let's go with 20 time steps and see how many we can freeze. And we successfully froze 88 out of the 100 qubits, which is pretty good. Let's see what happens if we try and freeze our qubits with fewer time steps. So this means that we'll be doing fewer measurements as our quantum state evolves. So if we again have 100 qubits, but this time only use 5 time steps, then this time we froze 60 out of the 100 qubits, which is less than the 88 that we got before. We can also go the other way around and try freezing the qubits with more time steps. Let's see if 40 will work. Now we got 95 out of the 100 qubits are frozen. So by making the time steps bigger and bigger, we can actually make our probability of successfully freezing a qubit as big as we like. And so the bigger we make the number of time steps, the closer we're getting to the situation of continuously measuring our qubit state. So we're not really giving it a chance to evolve away from 1. We know that we can freeze individual qubits using this method, but can we freeze entangled qubits using this method? So say we have 2 qubits that are maximally entangled, can we actually preserve that entangled state by doing continuous measurements on the entangled state? And I've turned this into another game of an entangled quantum freezer where we have to see how many entangled pairs of qubits we can freeze. So I've defined this entangled quantum freezer function. We used 100 before, so let's have a look at 100 again. 100 qubit pairs with 20 time steps. Let's see how many pairs of qubits we successfully froze, and we got 89 out of 100, which is extremely similar to our ordinary quantum freezer. One of the biggest challenges for building useful quantum computers is quantum error correction. This is where we find ways to ensure that a quantum state is not disturbed through unwanted interactions between the qubits and their environment, which is known as decoherence. The quantum Zeno effect has been proposed as a solution. If we continuously measure the state of a set of entangled qubits faster than they are interacting with their environment, then we can ensure that our entangled qubits remain in their original state. You may also remember that the quantum Zeno effect was essential for creating an 100% effective quantum bomb tester in my earlier video about quantum minesweeper. And if you've been keeping up with the Qiskit seminar series, there was an episode about universal control using the quantum Zeno effect. Despite the range of ways that the quantum Zeno effect has been applied in physics, there is still controversy about what exactly deserves to be called the quantum Zeno effect and the quantum Zeno paradox. In fact, a 1997 review about the quantum Zeno effect claims that what is actually paradoxical about the originally proposed thought experiment is that the existence of a detector can affect an unstable atom, even when it does not directly interact with the atom. And so experiments that show that you can freeze a quantum state through continuous interaction between a detector and the quantum system don't actually capture the essence of what is strange about the originally proposed thought experiment. The review ends with a positive note on the controversy surrounding the quantum Zeno effect. It says that although disagreement may be rife, we may remember what happened to Zeno himself. He was beheaded at Elea in Italy in 435 BC, and we may at least be grateful that none of those presently discussing the modern effect named after him have, at least as yet, suffered such a fate. I hope you enjoy seeing how many qubits you can freeze using Qiskit, and I'll see you next time for more quantum thought experiments. Bye!